I think we're going to get started. Sorry, guys. Hi. I think we're going to get started, everyone. Danielle Braun is going to speak first. Danielle's a research scientist working in the Bayes Mendel lab that she leads with Giovanni Parmigiani, so she'll be up first.
Great, thank you. So I co-lead the Bayes Mendel lab, and our lab focuses on creating clinical tools for individuals to identify individuals that are at high risk of developing cancer. So we focus on inherited mutations. Germline mutations have shown to increase risk of one or more cancer types. We focus on 2 cancer precision prevention goals. So one is pre-genetic testing. So our goal is to identify individuals who have a high probability of being mutation carrier based on family history, as well as their estimated future risk. And we have a set of tools that are part of the Bayes Mendel R package and are implemented in clinic for that piece of our work. And then the second is post-genetic testing. And so our goal is really to provide accurate cancer risk estimates for individuals based on their genetic testing results. So I'll talk through both of these kind of briefly, just the big picture of our Bayes Mendel models. So our models are Bayesian. They rely on Mendelian laws of inheritance. They take as an input from the user a pedigree. A pedigree is a family history that's collected usually by a genetic counselor. You can see here, it's a little bit hard to tell, but the person that comes in for counseling is indicated by this arrow. They report some family history. In this case, they actually have a mother that has ovarian cancer here, and they also have an aunt who's a twin of the mother, but she has breast cancer. And then they do have a sister that also has breast cancer. And so our models take this kind of information from the patient. What we do is we actually don't train our models on data. What we train the models is on published estimates in the literature, so we don't actually have raw patient data for training. And what we need from the literature are estimates of the prevalence of the mutation, as well as the penetrance, which is the age-specific cancer risk for carriers and non-carriers. So we have a set of single syndrome models. For example, BRCA-Pro identifies women who are at high risk of having the BRCA1 or 2 mutation based on their family history of breast and ovarian cancer. This woman has a probability of having a mutation of over 30%, which is considered quite high. Insurance companies still use these models and thresholds from these models, as well as other guidelines, to decide whether or not to approve the patient for germline genetic testing. A 5% cutoff is usually used, so this person would qualify for genetic testing. And our models are implemented in clinics, so we have more than 20,000 users of these softwares each month. These are 3 companies that use our models, and we also have an R package that's available for research purpose on our website. So, so far the models have been focusing on single syndrome, but we actually have more and more evidence in the literature that these genes that were once thought to be associated with just 1 or 2 cancers are actually associated across multiple cancer, increased risk of multiple cancers. So for example, BRCA1 and 2 are not just increasing risk of breast and ovarian cancer, but also pancreatic and prostate cancer and melanoma. So we are working towards multi-syndrome models, which would collect family history on a wide range of cancers and produce both the probability of having the mutation of many genes as well as the future risk of cancer. So that's kind of on the pre-genetic testing side. Post-genetic testing, so after a woman goes in or man for genetic testing, they receive back a result. It used to be that we used to only test for a couple of genes, so clinicians knew what to do with those results. Now, for the same cost, a clinician can order testing for a panel of genes. These are multi-gene panels. They can be up to 50 or 100 genes. And so what we've developed together with Kevin Hughes, our collaborator at MGH, is a clinical decision support tool to actually provide clinicians and patients the risk of developing the cancers that are associated with the mutation that the patient has. So for example, if a patient has an ATM mutation, you can select the age, so these are age-specific estimates. You can select prior surgeries or prior cancer that the patient has. And what we provide is actually the risk estimates for all the cancers that are associated with this genetic mutation. So having a mutation in the ATM gene increases your risk of breast cancer. The blue is if you had the mutation. The green is the general population risk. And also colorectal cancer, gastric cancer, and pancreatic cancer. So this is the overall risk by age 85, and we also provide the absolute risk age-specific So this is really important for actually clinical management. So for example, if this patient is thinking about having a mastectomy to reduce her risk of breast cancer, you can tell that she could probably afford to wait until her 40s until she does this. So we're really hoping that this can impact clinical decisions and behavioral changes for individuals undergoing germline testing. So just in terms of how we estimate these probabilities, so it's actually a massive literature review process. We have developed NLP algorithms to sift through the literature, and we have to do statistical analysis on the information we extract from the literature. Because none of the studies will actually report these curves in the literature. So this is widely used, so we have more than 10,000 times since its creation, about 1,000 times per month, over 30 countries. We have a couple of languages that we've translated it to. I just want to mention that we are shifting over towards the implementation side of things. So we do have 3 ongoing projects at DFCI to try to evaluate the effects of the tool, so among breast cancer and also among colorectal and Lynch syndrome patients. And in terms of outcome, we're looking at patient-clinician satisfaction, really understanding of risk, and then behavioral changes. So most importantly, we are kind of in the process of growing in terms of ASCME and Bates Mendel. So we do have a couple of paid RA positions for master level students if anybody's interested both in terms of the statistical modeling, in terms of the implementation of the models in the clinic, some data engineering work. Also, we do a lot of methodology. I didn't describe any of the methodology type of questions that we do in our lab, but we do have a lot of PhD and master students that are working with us. And we're also hiring a full-time master level statistician related to ASCME. So feel free to reach out and contact me.
Does anyone have any questions for Danielle?
Can I ask you about the input data that you use to train the model? Like, so you use just the literature, right? So what is like the ground truth, like on which like you can test like your error, or maybe input the model? Because like I suppose in the literature you don't have patients, or you just have like association or this mutation, this paper, this.
Yeah, so training, we estimate these model inputs from the literature, but validation, we do have patient data with family history, which is actually one of the RA positions, is actually sorting through this family history data. It's messy, it's in terms of the format, in terms of how it's collected, in terms of linking individuals, because you need to really create links between family members with father, mother IDs in the family. So we do have validation data. Unfortunately, it's not large data sizes that we hope to have in the future, but we do have some. And for that, you need testing results as well as family history.
Thank you.
Ideally, for future risk, you need to follow them up over time and see if they actually develop cancer, but that's even more challenging.
So what are your uncertainties in your predictions?
So that's another good question. So these parameters that we estimate, both the prevalence and the penetrance, have some uncertainties with them. When we do estimate these parameters, and we try to do our own meta-analysis, and actually Kathy is here, this is a figure from her work on a likelihood-based approach to do meta-analysis for these penetrants, so we do have some uncertainty estimates for that. It can be propagated into the model, so you could report to a clinician that the probability that the patient in front of them has a mutation is 30% with a confidence interval. It's really difficult to communicate risk to patients and clinicians, and so we don't, but of course there is uncertainty associated with these estimates. We're aware of it, but it's just how do you communicate that?
Yeah, but generally if you just like communicate one number, it's not much of use. If your confidence interval is like 20% plus minus, or if it's 5%, it's a very different statement. Right,
and one thing to note is that our model is one of a few that's implemented in these softwares, so most clinicians will see in front of them actually predictions from multiple, so at least there's some range that they do see, even if none of the individual models, including our own, don't actually report the range, but they do see a range across the different models that allows some sort of.
You say you kind of get estimates of point prevalences of genes best.
For what?
Of the genes. Is there any kind of correlation structure? Does that cause any problems?
So no, so we assume independence across genes, which I think is safe assumptions for these for the genes that we're looking at. So yeah, it's also very, very rare to have mutations in multiple genes. But,
how much pedigree information do you typically have?
yeah. So the good news is that like this software, actually most of the software that uses our models, and there's also the software that we then get back data from. They have the ability to collect quite extensive pedigree information. It really depends on the setting in which the information is collected. The genetic counseling clinics will actually spend a lot of time and collect pretty detailed pedigrees. Various other data sources like mammography screening clinics, they'll only ask about affected relatives and not about unaffected relatives. The unaffected relatives can be informative because if you have a lot of relatives that survive cancer-free until a later age, you're less likely to have the mutation in the family. So it really varies. We've toyed around our group with like various versions of the models that are kind of light versions that take only first-degree relatives and or only limited family history. You do lose accuracy, but it's not too bad in most cases.
Thanks, Danielle. So we have Tamar Sofer next. She's a former student in the department, now an assistant professor over at the medical school and working at the Brigham as well.
Okay, so I will tell you about challenges in association testing in whole genome sequencing datasets in diverse population, but this is not going to be a deal because I can't give you many details in a short time. So a little bit about genetic data. So our DNA is a sequence of nucleotides, GA, CT, across 23 chromosome pairs, so we all have 2 chromosome 1s, etc. Genetic variants are those that change or vary between people. So for example, if you look at these subsequences that I have here, all the black ones, this is person 1, copy 1 of chromosome. All the black ones are the reference, and G here is about vary. So this is a variant, basically all the blacks are reference, and we count the ones that are non-reference. So here we'll have 1 or up to 2 if a person have 2 non-reference alleles in the 2 pair of chromosomes. And we know that some variants are more frequent than others. So, for example, we may have multiple non-reference or just a little bit. For example, these variants are not variants in our sample because they're the same for all people. But if we had more and more people, maybe someone will have a variant over there, and this will be rare. So these are rare variants. So actually, most genetic variants are rare. So testing association with rare variants is challenging because asymptotic properties we'll talk about in statistics do not hold, and correct modeling is critical. I'll now do a demonstration when we're testing rare variant association with binary traits. So this is a 2x2 table in which I simulated data and put them there. So I simulated 1,000 people with 11% disease probability, and I simulated a rare variant that is independent of the disease status. So here we have non-carriers of the rare variant that have disease, carriers of rare variant that have disease, non-carriers of non-disease, carriers of non-disease. And now I'm going to turn this 2x2 table into a regression figure. So I put these numbers on the sides, and now I'm adding the y-axis with disease probabilities. This is the true regression line, the disease probability as a function of rare variant status. We only have 0 and 1, so the line is straight because the disease status, the disease probability is independent of the carrier status. And then we have this point here, which is the case proportion in non-carriers. This point is the case proportion in the carriers. And this is the estimated regression line based on this simulation. And now we're going to do a few more simulations and look what happens to the regression lines. So here the regression line kind of follows the true theoretical line, and here it goes down and up and up and down. And we see that this point here is always at around the same place, but this point kind of fluctuates a lot. And the reason is that this number is not stable, because there are so few carriers, because the variant is bare, the denominator is small, it leads to a lot of variability. And this makes the regression estimator unreliable. So I developed association tests that do not rely on unstable properties, which standard statistical tests rely on. So I developed robust tests for rare variants. The other thing that I'm going to show you is about how properties of genetic variants, which are exposure in our regression models, in combination with properties of the outcome, have large effect on statistical tests. And we're not used to thinking about the exposure being problematic, but it actually is. So I'm cutting to some results. These are QP plots of p-values on the minus log 10 scale. So the higher the values, I mean, the more significant it is. So from whole genome sequencing analysis of BMI, and the QP plots compare the p-value from the analysis from the p-value from the theoretical null. And I'm comparing tests using different models of the outcome variance and sets of genetic variants with specific characteristics that I computed. So here, for example, I used some mathematical derivation and I computed on a set of genetic variants in the sample that I studied, and I found genetic variants that I figured they must have underestimated standard errors for their effect estimates if I used a naive method to analyze, to test their association with BMI. And indeed, we see that the naive method that I call the homogeneous variance shows this inflation. So the p-values are too significant compared to what they should be. This is a similar example, but the opposite way. So according to my computation, I expect that these variants to have overestimated standard error, and indeed, if you use a naive model, you see that the p-values are too high. So this is called deflation. So, final slide. In my work, I optimize both computing and statistics. So testing tens or hundreds of millions of genetic associations takes time. Longer time the number of people is large, and also more people, more variance. So good methods optimize computing time and memory and statistical properties. Simple yet clever statistical methods, once elegant, are preferred. So you need to love and understand both statistics and computing to do what I do, and let me know if you do.
Does anyone have any questions for Tamar?
Yes.
Coming back to the first slide, we talked about variance of in the gene. Presumably, like
You mean this?
that only works for when you have basically swaps between. Presumably, there are other measures for when you have insertions and deletions.
It's true. Yes. Kept it simple. I didn't give enough details to ask questions.
That's all right. All right, thank you, Tamar. So we have Christine Choirat. I think I said that right. Up next, she's the Chief Innovation Officer at the Data Science Center, the Swiss Data Science Center, and an adjunct lecturer here and at the Extension School.
Yes, so I start too. So thanks for having me. So I'm going to say a few words about the Swiss Data Science Center that I joined recently, and about Renku, which is a platform, an open platform for reproducible data science. So as a forward, like there's domain science, data providers, and they are very often different with different agendas and different incentives. So as maybe a clinician, you want to find the best drug. As a data scientist, you want to find the best hyperplane. And as a patient, you're quite worried that your data is going to be shared with people who should not see it, right? And so we are trying to federate all these three categories to create scientific breakthroughs. And to do that, we fund academic projects and we have industry partnerships. So it started almost 3 years ago. It started with 3 people, now we are 60 growing. So everybody's hiring, I'm hiring too. And so we are based physically in Lausanne at EPFL and in Zurich at ETH. And we have like 3 big missions, so like academic and industry partnerships, so about 30 projects that are ongoing. We're a grant funding agency. And we have particular emphasis in personalized health, environmental science, digital manufacturing. We have industry partnerships. We contribute to education in data science, so master degrees, executive education. I teach here. We coach for industry partners. And then we have a platform which is called Renku. So it's Japanese, it's poetry in Japanese, don't ask. And so it's open source, it's free, it's available for everybody. And we're trying to be for data science what DIT is for code. And so, so you may heard that there's a reproducibility crisis. A crisis would mean that things were better before and then they got bad. No, they've been bad all the time. And so the academies have published this document last spring, I think, where they say that we all should be worried about reproducibility and replicability, that it matters. And that, you know, researchers, agencies, journals, the NSF, everybody should work on making research and science better, right? And so there's a YouTube video which explains like the 2-minute take-home message, like difference between computational reproducibility and scientific replicability, fine, all good. Then it's important for institutions, journals, funding, everybody to work together. Yeah, that's great. And how do you do it, right? I was aimed for here, like I was aimed for reproducible methods type of stuff. So how do you do it for real? Responsibility begins with you. So that's the problem. Like we tell you that you should do something, but we don't tell you how. So figure it out. So document your tools and your methods and write README files. That's not in it. So so what the Swiss Data Science Center did is we have a team of 12 to 15 people full-time, putting together all the tools that you would need to work on to have a reproducible work, like your code, your data, your compute environment. So all the solutions exist. So we selected out of those for you not to have to think about tooling and being a software engineer, but to be productive and worry about science, not about tooling. And so in practice, it looks like something very, so we combine technologies that are Jupyter or Studio. So as a user, what you would see is a Jupyter Lab interface or an RStudio interface. We can make sure that your interactive session is exactly the way you want it to be. We can connect to data repositories so that you can import data from generic or domain-specific repositories. But under the hood, we use Docker to create containers for your compute environments. We use GitLab to keep versions of your code and to have continuous integrations and good software engineering practices. We generate a common workflow language pipeline so that you can rerun at scale. And under the hood, there's a knowledge graph. So you can actually mine all the knowledge that is created in your project, across projects, and what data is popular, what algorithms are good, etc., etc. And the knowledge graph, which is the core of Renku, is something that can be as simple as this. So you don't see a lot, but like I simulate data with R, I keep track of my outputs, then I have another script to plot my data, then I can actually see that this plot.pdf file, I can see how it was generated. I can rerun the same pipeline with different data, I can share it, and I can do all these sort of things, right? And so it's open, so it's renkulab.io. It's renkulab.io, and I have to confess, I made the wrong guess about the music you are going to use. I expected a cow. Oh. Yeah. scientist, master level, PhD, postdoc, industry. If you do genomics and proteomics, write to me. I'm interested. Yeah.
I have a question about this knowledge graph.
Yes.
Like, like a big innovation also when you want to search maybe,
Yes, absolutely.
data, related work.
Yeah.
And I was wondering, do you also have it on a more abstraction level that you can even say, something about the research findings, or, that you can maybe embed it in a kind of more abstract knowledge base that might also help for, searching for scientific findings?
Yeah, that's the objective. Like here I'm representing the technical stack, but the idea is really to mine a knowledge graph, like to get insights on, like, say, which methods work, which methods don't work, which ones are popular, which one would be recommended. Really have a social aspect to. So Renku is actually federated. We can actually search across different deployments. We're deploying in production. We're open. We can give it a try. But yeah, that's exactly the objective, so that we can follow the whole data-driven pipeline, like from data acquisition, data repositories, to all the way to the publication process. This is for science in the making. This is not for archival, but that's really exactly the idea to search for knowledge so that it doesn't get lost. Yeah.
So this would only be for publications, so official publications, or can it also be for, I don't know, you have negative results, and for instance, would you say, okay, this doesn't
It's for
work?
you.
Ah.
I use it to teach, for example, so that I can tell my students, open a notebook, this is a lecture about Git, this is a lecture about parallel computing, or about, hierarchical models, or whatever. So no, it's for anything, and then you choose what you share. You don't have to, actually, it can be totally private. Yeah.
Yeah, I was wondering if you have that diagram, right, so that the pipeline, I feel that everyone is sort of hacking code, right, to sort of make it work on that application, right? So I was wondering, like, how likely is it that something like this actually works in practice? If you feed another data set, it's not going to work
So
right away. Right?
it's like, the mindset is really the cat herding type of mindset, meaning that what we provide is version control, and if you, for code data and environment, and what I mean is that this part is not compulsory. You can make it work, but you can still do reproducible science without pipelines. So this is like, you can do your own science marginally belonging to the knowledge graph. We're not forced, and that's a great question actually. It's like, here it takes self-discipline. If you don't have self-discipline, we already provide like a backup plan so that at least you have Git and Docker, right? It's like, and then we will work with you to make pipelines work. Because at the end of the day, they tend to be more, easier to extend and maintain when they're well written, which is very hard. Yeah.
Let's say if I have a given workflow on GitHub, what are the obstacles in porting it to Renku?
None, because you can very, very limited. So depending on the complexity of your workflow. So if you have a workflow where you have a part of your pipeline that uses Unix tools, and then Python, and then R, I would recommend you have 3 different projects, so that you have one Unix, one Python, one R. We can mix, right? But and then it's already under Git. You have Renku in it, your Git repo, and you're good to go. So, and if Renku disappears, it's fine. Well, not for me, but it's fine because all the tools that we are using are, industry standard or open source standard. Everything is open source, so you don't lose anything by using the tools. All the formats that we use are just absolutely common. Yeah.
Can I ask a little bit? This sounds quite ambitious. Is it something you are planning to sell or open source?
No, absolutely not. So it's open source. The development is guaranteed by federal funding from the Swiss government through the ETH board. So we are funded, I'm on camera, but I would say 99% sure for the next 5 plus, I would say 10 years. And the idea is that we are going to use it in Switzerland, and we want people to actually know about it before they go into solutions where you have a vendor overkill type of situation. So it will never be sold, at least the base, if it's Apache. So if a company decides that they want to sell a customized version of it, this is not our concern. It's legal to do it, but the core of it is ETH, academic center type of stuff, and everybody can use it. We have a cloud deployment in the Swiss cloud. Anybody can use it to give it a try. And then actually I'm in talks with several institutions in the US and in Europe to have deployments.
What is the closest paid competitor for this platform?
Closest competitor.
Paid.
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 Maybe CodeOcean. Maybe Domino Labs. I'm not really sure because it started like I would say a long time ago. It's been like 3 years in the making, and it was like, believe it or not, but it's still in relative isolation in a sense. Like you have a team which is like trying to focus on the features and not on monitoring what other people are doing. And certainly not in startup, like let's do VC, let's get Series A type of mode. So yeah.
So I understand, sorry. Is it free? I mean, all the computational power is free?
Yes,
I
at the
mean, I
moment.
can apply and
No,
I
you
have
don't
free
apply, you log
computational.
in. Because at the moment we're just, it's like the bootstrap type of mode. I
It's like
provide
what is like
resources.
the-
I
sorry.
provide like 1 to 4 CPUs. I provide like a couple of gigas of RAM, and then you're good to go to give it a try. If you like it, you can ask. If you want more, you can ask your institution to deploy, or we can work on having a service where you would pay no cost recovery. You just pay for the compute. We used to have GPUs for free. That was not a good idea. You knew it. You knew it. Yeah, and it's not restricted to Swiss researchers. We really want it to be international, and like, I'm not Swiss, so I can say neutral, you know, like really neutral.
And what did you like the upper bound for data storage, more or less?
But you can actually, we have like not the version that you have online, but like on the roadmap, we really want researchers to be able to mount their own resources. Like if you have data on S3, or if you have like data on your server, we are not going to ask you to copy it to the platform. So I want to find ways to like somehow stream or whatever technical term is, and so that there's no limit, because we can be as simple as I do a PDF in R, or I work with, you know, at the national scale genomics or proteomics, and we're talking really a lot of data. Even if, like, for the record, Switzerland is like as many people as New York. Anybody from New York? But like to give you scales, like it's still a country, it's still complicated, it's still a lot of data. But yeah. So give it a try, shoot me an email, send me your CV.
Thank you, Christine.
Thank you.
And we have Georg Hahn up last. And Georg is a research associate working in the department with Christoph Lang.
Yeah, hi, I'm Georg. I'm with Christoph since July. And I just want to use that lightning talk to sort of do a tiny overview over what I've been doing in the past and what we're currently doing. And even though this is 5 minutes, I still wanted to put a summary slide, which is about sort of the main interest of mine would be summarized as algorithmic statistics and sort of algorithm general population stratification is what I present, which is what we do right now, together with Christoph and sharing notes. And I have a major interest in multiple testing, and I will also talk about something slightly unrelated, which I think are problems, sort of just interest of mine. Here's what we do right now. We're looking at sort of whole genome sequencing, genetic association studies, and we want to identify population substructure in order to sort of account for or correct for confounding, for this confounding source. And here would be an example where we have a genome from like a sort of data chromosome from the 1000 Genome Project, some similarity matrices that sort of we run on like Windows, and you can see that there are some, also these lines sort of show some local to global correlation, and this plot is just sort of to show that there is some possibly local to global correlation going on. We're trying to find out what exactly that means and what you can do with it, because local has not been looked at so much, and we have sort of two things that we're working on this. And another thing that one could do is these population stratification plots along different subpopulation groups. Surely you've seen that before. That would be on a global level. On the other side is on a local level. Again, something that we try to sort of make some sense of, because these look pretty similar, but they do not have to, and we're trying to find out what the local level will give us in that sense. So that's what we're doing right now. And then we have another one on smooth lasso. So penalized lasso, or like regression, is something you surely came across. It's convex, but you don't have a gradient everywhere, not necessarily. And so this would be an example where you sort of, the idea is to sort of smooth another function around it in sort of an epsilon environment like here, so that you always know how far it is away. But in contrast to the original function, this one here has a gradient, and you can sort of use it to use this guy's method to minimize it. For example, in that plot also. Yeah, that would be sort of a tiny overview. And another major interest of mine would be testing, which was symbolized through that extremely happy p-value in the first slide. Here symbolized through, for example, area testing, drug testing, sort of performing a lot of tests at the same time. And there are a lot of challenges that you can do. If you, for example, look at that scenario where you assume that you have to sort of approximate p-values, you don't know what they are in practice, you have to do bootstrap or permutation testing. And then questions which arise, for example, could be, how can you like, what can you say about the result? Can you say surely rejected, surely non-rejected, maybe some undecided ones, give guarantees of correctness, runtime results, finite runtime results, or also what is sort of the optimal, like that last plot here shows something like the optimal allocation of samples, where this is sort of some threshold, these are some p-values, this is the crossing point, these would be non-rejected, these would be rejected, and this line here sort of shows how you should allocate your effort. And the question is sort of how do you get to that, right? Like, what is the optimal allocation of samples? That would be another thing. And I did, that's what I did before, and sort of there's sort of a variety of papers on this. And then my last one is that NP thing, so symbolizes that extremely happy NP hard problem in the middle. And you have sort of something like the TSP, traveling salesman, or maximum click. These are popular problems that also arise in certain applications. If you look at anything with graphs, for example, or machine learning, it's very likely that something like this pops up, more or less, unless it's a very simple graph problem, then you can possibly solve it in polynomial time. And this slide, again, this slide's everything. It's just sort of to show that you can do a lot with them. So you can, for example, split them up into tinier problems, such that if you solve both, you get the solution to the other one. How can you split those problems? How can you infer information from other problems? So you look at other problems and that tells you something. How can you approximate them, or how you can partially solve them? So you only like exhibit or like resolve certain variables in your solution. All these things are possible. And again, I've been doing that for a couple of years now, together with Los Alamos National Lab in like a variety of publications, and also recently with Lawrence Livermore National Lab in the Bay Area. And that is 10 out of 10. And I'm done even before that.
Oh yeah, 20 seconds.
Oh, sure.
When you say look at local substructure, what does local mean? Like in which sense do you use?
So local would be, for example, that you correlate windows against other windows, or like a subsection to the flow. Like you have something like you need something like to summarize the data, for example, by computing some kind of genomic relationship matrix and then some eigenvectors or two eigenvectors, and then you want to get some summary, some comparison measure, for example, correlation or L2 norm or something between those, and you run that across the windows and overall, and you want to see how similar it is on a local level compared to the global level.
But so local then in the spatial sense? Or
Yes.
Okay, but in some way, like DNA has also some 3D structure where spatially, if you put it on a line, spatially,
I see. Yes.
may be very close to each other in the actual space. Right?
That's a good point.
So maybe local might be understood in an embedding, in a different type of embedding.
Sure.
In a different space.
Sure.
So for the smooth lasso,
Yes.
so I see that you want to do smoothing so that the bias, like you can cut down the bias, right? Like that is the motivation behind smoothing the lasso?
I guess it would be more that to be able to process large data sets. So you have something that you want to sort of perform, for example, that estimation or computation of that estimator on very big data, and you want to facilitate this by using, for example, a gradient descent or something with non-numerical gradients, so with explicit ones. So you smooth first in order to be able to nicer locate that minimum, and you want a guarantee on how far you're away, because you actually minimize some other functions.
Okay, and
That would be the idea.
so then about the dimension reduction of the lasso, so if you are using the smoother parts,
Sure.
so like how does that part form?
What do you mean?
So like when you are using the yellow and penalty, and then like that is why you can have a sparse solution, and if I am using
I see what you're saying. Yeah, that's a good one. So that's actually a very good question. So that would definitely be something we haven't looked at, where you plug it. I mean, you sort of plug it into the original L1 function, right, to like see what comes. Yeah, I see what you mean. All I can say is that the idea would be to know that the two minima are not too far away. So if you have that vector, at least you know that the components won't vary too much compared to the other one. But I guess it comes at the expense that possibly some are not exactly zero, like zero anymore. So you might maybe one should introduce some threshold or something.
So you
That's
are
what you
just
meant, right?
trying to locate the actual minimum, like maybe not the one using the original vector, but you are trying to go close to that, like and then from there at least you can get a good initialization.
Exactly. And that can be useful because sometimes it's hard to even get there. So we have some plots where it's advantageous to use that smooth function in order to get to a good minimizer first. And even though that might not have that L1 property, as you said, if you then compare to, let's suppose you generate some truth and then you try to recover that again, that vector that you get out of the smooth one could be closer in like correlation or some other measure than if you just perform the minimization on the L1 penalty, just because that's harder. So your result will be worse. In theory, it's all good, but in practice, maybe not.
Okay, thank you everyone.
Cool.